Lesson 3, relationship between sets. The first one is singleton set. This set contains just one element or member. For example, set A equal to S, such that S is the president of Nigeria. Therefore, A is a set of S such that the country Nigeria has one president at a time. That set with only one element or member is called singleton set. The second one is finite and infinite sets. A set B which has only a finite number of members, that is, countable elements, is called a finite set. Otherwise, B is an infinite set. If the elements of B are uncountable, B is said to be infinite set. The number of elements in a finite set B is called the order of B and is denoted as this. So this is order B, the number of elements in a finite set. Examples of finite sets are as follow. Example 9, you have set B, days of the week. They are countable. Set C, people in Nigeria. They are countable. Set D, that is example 11, even and odd numbers less than 1,000. They are also countable. So all these examples are finite sets. Examples of infinite sets are as follow. Number 12, set E equal to multiples of 4. If you are asked to list all the numbers that 4 can divide, the list is endless. So it is an infinite set. The number of elements in set E is equal to infinity, no end. Example 13, set F equal to S such that S is less than or equal to 5. All the numbers less than or equal to 5 cannot be listed. The list is endless. So number of elements or members in set F is equal to infinity. The next relationship between sets is subsets. Let A be any set, then a set B is called a subset of A if every element of B is an element of A. If every element of B is found in set A, then B is a subset of A. The notation this and this are both used to mean B is a subset of A. According to our definition, a set A is always a subset of itself. That is true. All the elements of set A, they are also in set A. So A is a subset of itself. Any set B of A which is not equal to set A, any set B of A which is not equal to A is called a proper subset of A. That is this notation. If A is a subset of B and also B is a subset of A, then A is equal to B, because then every element of A is an element of B, and every element of B is an element of A. That is a form of vice versa, and as such, the two sets are said to be equal. The diagram below illustrates B is a subset of A. You can see that all the elements in set B are inside set A, the larger circle. A is represented by the set of all points inside the large circle, and B by the set of all points inside the small circle. All the elements of set B are contained in set A, and as such, B is a subset of A. Figures of this sort are sometimes called Venn diagram. We have that in our subsequent lessons. For example, number 14, let set A equal to this, set B equal to this, set E equal to this, and set F equal to this. Then the following are true. B is a subset of A. All the elements, not all, some of the elements in set B, A, B, C, are also in set A. So B is a subset of A. A is also a subset of B. E is a subset of A. All the elements in set E are also in set A. Set A is also a subset of set E. E is a subset of B. B is a subset of E. And again, A is not equal to B. That is true because of element T. A is equal to E. That is true. B is not equal to E. We want to check the order of the finite set A equal to E. The order of set A is equal to order of set B, E, and that is 3. You have 3 elements in the 2 sets. Then the order of set B, the number of elements in a finite set, is the order, and you have 4 elements in set B. The next relationship is the empty or non-set. A set is said to be non or empty if it has no elements. No elements at all. It is denoted as this. That is the phi notation or the empty brace bracket. Note that this set is not a non-set because 0 is an element. 0 is an element. The empty set is counted as a finite set with the order equal to 0 because no element is in it. We regard the empty set as a subset of any set. The empty set is a subset of any set, let's say set A. An assumption which does not contradict our previous notation of subset. For the statement, the empty set is a subset of A should mean if S is a member of the empty set, then S is a member of A. If S is a member of the empty set, then S is a member of A, because the empty set is a subset of any set says A. Since there is no S such that S is a member of the empty set, this last statement is never contradicted. Example 15. List the elements in the set S is prime such that 24 less than equal to S less than equal to 26. Solution. If you check the given range, there is no prime number between 24 and 26. Number that has two factors, 1 and itself. Such numbers or such a number is not in the given range. Hence, the set prime numbers between 24 and 26 is an empty set. The next relationship is disjoint sets. Two sets, A and B, are said to be disjoint sets if they have no element in common. That is, their intersection A intersection B is equal to empty set. If A and B have at least one element in common, they are called non-disjoint sets. That is, the intersection of A and B is not an empty set. Look at this diagram. You have the set A and set B. The two sets have no point of intersection. As such, A and B are disjoint sets. Example 16. Consider the sets A equal to with elements A, B, P, and set B with elements C, E, K. If you check set A and B very well, they have no element in common. That is, the intersection of the two sets is an empty set. For that reason, sets A and B are disjoint sets. They have no common elements or element. We have the equal sets. Two sets, C and D, are said to be equal if they have the same number of identical elements. The key word here is identical. The equality of sets C and D is denoted by this: C equal to D. Here, the order of manner of arrangement does not matter. For examples, number 17, if set C is equal to this, set D is equal to this, then C is equal to D. The elements are identical, even though the order of arrangement is not the same. Number 18, if P is equal to this, K is equal to this, then P is not equal to k, even though each set contains 3 elements. But the 3 elements of P are quite different from those of K. In such a case, sets P and K are not equal, but they are equivalent sets. The next relationship is equivalent sets. Two or more sets are said to be equivalent if they contain equal numbers of elements which are not necessarily identical. That is, two sets are equivalent if their cardinal numbers, the number of elements, are equal. In example 18 above, sets P and Q are equivalent since they both have 3 elements, though not identical. That is, number of elements in set P is equal to number of elements in set K, and they are 3 in number. The symbol for equivalent of two sets, say A and B, is written as this. So the double head arrow is used to denote the equivalent of two sets. This sign is also called the implication sign in logical concept. Example 19. State whether or not the pairs of sets below are equal or equivalent. Set A equal to English vowels. Set B equal to the elements A, U, I, O, E. Set C equal to S is a subset of N such that 6 is less than S, less than or equal to 10, and D equal to S, subset of Z such that -2 is less than or equal to S, less than 2. N is the set of natural numbers and Z set of integers. Solution: set A is the set of English vowels. You have A, E, I, O, U, and set B equal to this. If you check both sets, they are equal because the elements are identical, and they are equivalent because they have the same numbers of elements. Let's move to set C. In the given range, you have elements such as 7, 8, 9, 10. This is less than 6, so from 7 to 10. And set D, in the given range, you have these elements. Both sets are not equal because the elements are not identical, but both sets are equivalent because they have the same numbers of elements. We also have the power set. This is the collection of all the subsets of a given set. It is denoted by 2 to the power of n, where n is the number of elements. Example 20. List all the subsets of set A. The elements are 1, 2, 3, and they are 3 in numbers. That means n is equal to 3. So this is the given set. N is equal to 3, the number of elements. The power set becomes 2 to the power of 3, and that is 8. That is, set A has 8 subsets. The list is the first subset is the empty set. Then you take the individual elements, that is 1, 2, 3. After that, you pair the first element 1 with 2 and 3. You have it in this form. You pair the second element with the third element. You have it in this form, and the set A as the last subset. Remember, we said that the empty set is a subset of any set, and any set is a subset of itself. When you count, you have 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 subsets. That is the power set concept. We also have the universal set. The universal set. The universal set is called the mother set because all other subsets emerge from it or relate to it. If we define the set of natural numbers as a universal set, then we can define the subsets of even numbers, odd numbers, prime numbers, multiples of numbers, and so on. So all these subsets emerge from the universal set, the set of natural numbers. Another instance is this. If we define the country Nigeria as a universal set, then we can define each state as a subset of Nigeria because each of the states are part of the country. Universal set is denoted using any of these symbols. Example 21. Consider the set S equal to S such that S is obtained by tossing a die once. List the elements of A equal to odd numbers, B equal to even numbers, C equal to prime numbers. Solution. From this example, S is the universal set, and it is by tossing a die once. A die has 6 sides. If you toss that die once, either 1, 2, 3, 4, 5, 6 can show up. So you have the universal set. From this set, we have the subsets A, B, and C. Subset A, odd numbers. Odd numbers in the universal set are 1, 3, 5. Subset B, even numbers, they are 2, 4, 6. Subset C, prime numbers, they are 2, 3, 5. Note that the universal set and the empty set are called the special subsets of the universal set. End of lesson 3. Thanks for following to the end. Don't forget, watch out for more from the voice of Peter Kos. If you are not saved, your life is in crisis, your life is in trouble. To avoid all of that, you have to give your life to the one that can save you, and that is the Lord Jesus Christ, and confess him as your Lord and personal Savior every day of your life. If you are saved already, congratulations. Live righteously and be prepared, because on the last day, some will be taken and some will be left. Be good to yourself. Stay out of trouble. Study your books. Do the needful at all times. Flee every appearance of evil. Don't defraud others to make money. Find something good and genuine to do with your hands and your brain, and the Lord will bless you. Goodbye and stay tuned.